Alrighty, welcome back to 105. So we saw some sorting algorithms last lecture. Should be able to at least understand them, maybe come up with them, code them. So today we'll be going over more sorting and how to use some built-in sorting functions in C, which is a bit ugly, but we have to understand pointers and all of that stuff. So let's get into it. So the things we touch on in today's lecture, not really testable. They give you a little flavor of what happens in 244 and some actual algorithms that you would actually use to sort numbers or sort anything in an array. Specifically, what we will talk about is called quicksort, and it is a big O n log n sorting algorithm. So how this works is, well, it uses recursion. So the whole idea behind this is we want to break our problem down into a smaller subproblem. And what we're going to do is select an element as a pivot value, and we're going to essentially sort around that one value. So we want to place that pivot value such that all the elements to the left of it are less than, and all the elements to the right are greater than. So we don't have to sort the entire thing. We just have to do that step and then do that step recursively over and over again, which is just called partitioning, because we know that if everything is less than that number to the left and greater than to the right, then at least that one number is in the right place. And then after that, I can recursively sort both sides. So, to just spoil what the algorithm looks like, well, quicksort, again, it's sorting an array, so it takes an array length, and then we write a recursive version of this program. We need a little helper function because we're recursively dividing that array into smaller and smaller arrays. So in this case, our quicksort helper, well, we add arguments for like the lowest index and the highest index. And then in our helper, we just say low is equal to 0, high is equal to array length minus 1, the greatest index in this array. And then our recursive function would be like, hey, if low is greater than high, so or equal to, I don't have to do anything. My array has one element or my bounds are switched around. Otherwise, I find the index of my pivot. So I partition the array such that everything to the left of this pivot index is lower, everything that is to the right of it is higher, and then, well, that one pivot is sorter, so then I can recursively sort the other half of the array, so the half that is less than this pivot, which would be low up to pivot minus 1, where pivot is the index, and then sort the right half of the array, which would start at pivot plus 1 all the way up to high. So kind of like the Towers of Hanoi implementation we had, we're sorting it into two smaller subproblems. So the majority of this comes to how we actually implement this pivot or this partition function. So to step through as an example of just how we would implement the partition, well, first, there's a whole lot of different ways to pick the pivot values and different trade-offs you would have with that. So the way that I'll show you how it's implemented and usually implemented, or the simplest thing to do, is to just pick the last element as the pivot value. So I'm picking the value 9 at index 7, so we're sorting 8 numbers here. And then the green arrow is keeping track of where that pivot should go. So if I immediately move this 9 here, if I swap the two values, that means everything to the left of that should be smaller. So we'll initially say the pivot is equal to whatever the low element is, and we'll just step through every element. And if it is less than the current value we're using as our pivot, which in this case is 9, we'll swap it there and then move that green arrow, which is indicating where we should place our pivot value. So if I go through this, what I want to do is, okay, well, compare the pivot value with the value I'm currently looking at. Well, it's greater than what I'm looking at, so I don't have to move it. This would be where I would place my pivot, because at the end, I'm swapping my pivot with whatever is at the green arrow. If it's greater than, the bigger element will go at the end. It will be to the right of the pivot, which is exactly what I want. So next, I would look at 14. Again, that's greater than my pivot element, so I don't have to do anything. Now, I'm looking at element 8. Oh, well, that's less than my pivot, so I want to make sure that comes before it. So I need to swap this 8 with the 10, and I need to move where the pivot should go up by 1. So I would do that. So I would swap those two values, move my pivot up to 1. So now if I stopped here, assuming that's the rest of the array, well, I can move my pivot to, like, swap my pivot with whatever's at the green arrow, and I know that, hey, everything to the left of my pivot is definitely less than it. But in this case, I have to still scan the rest of the array. So I'd look at 13. It's greater than my pivot, so I don't have to do anything. Next, I look at 20, greater than my pivot, don't have to do anything. Now I look at 3, it's less than my pivot, so I'm going to want to swap the element 3 with whatever is at the green arrow, which is larger than me. Again, we want to keep track of where I should place this element 9. So I need to swap 3 and 14 and then move up my pivot by 1. So it would look like this when I am done. Now, I still have to keep track of the last element. So we'd compare 6 with the pivot value of 9, and oh, that's less than it, so I need to swap 6 with 10 and then move up this green arrow. So at the end of this single iteration of partitioning, I'm done, and all I have to do as the final step is swap my pivot value with whatever is currently at the green arrow. So I swap the value 9 and 13. Now I'm done, and I can see that I didn't have to sort the entire thing, but now everything to the left of this value, so 8, 3, and 6 are less than, and everything to the right is greater than. So 20, 14, 10, 13. So I know this 9 is in the correct place. I don't have to argue about any other values, and then I can just recursively do it on either side, and eventually it will be sorted. So everyone kind of see how that works? So that's the whole idea behind quicksort. So again, I showed you this code. This is the recursive, kind of easy to understand part, and all the kind of nitty-gritty details are in this partition function. So one implementation, if you look it up on Wikipedia or something like that, you'll probably see this as the algorithm, which has a lot of really weird things kind of going on. So they saved the pivot value as whatever the element is at the very end of the array, and they temporarily set the pivot index equals to low -1, which could go easily out of bounds. Then they start at j equals low, so something in bounds, less than or equal to high. So it will actually go up until j is equal to high. So it will actually check its own value. And then if it's the current element is less than a pivot, then before it does any swapping or anything like that, it will move up I and then do the swap. So now we see we won't go out of bounds here because it might be, I might be -1 in the worst case, and then before the swap we do ++ I. So we move it up by 1. We wouldn't go out of bounds here. Swap the two values, and then at the end, there's like a weird thing where I have to adjust the I by 1 to make sure that I'm actually pointing at the right value I need to swap with. So I don't really like this implementation. The one that I like, if you want to make it a bit clearer what's going on, that closely follows the example and doesn't have as much going on, well, we started off the same. We can have the pivot value equal to the array at high element and start I is equal to low. And then we can have j equals low and go till j is less than high, so we don't have to check the highest element. Again, same check. If the value is less than the pivot, we can have a little special case here to make sure that we're not swapping the last value, like we're not swapping the current values around if they're pointing at the same index. So I can swap them around, and then this is that step where I adjust the pivot at the end, like I did in that example. And then, just like in that example, just when we make it through the loop and we've inspected every single element, then we can just swap the pivot value, which is at array high, with wherever we found it should go. And then we return I, which is just the index of the pivot. We know for sure it is in the right spot. So everyone kind of okay with that? You never have to implement, you never have to do anything. This is kind of a relax and look at stuff lecture. All right, then we will do something stupid then. So there's also some joking sorting algorithms. One is called BOGO sort, which kind of work, quote unquote, but you should never use. So the whole intuition, if you can call it that, behind BOGO sort is, say you were sorting a deck of cards. How you do this is you throw them up in the air, you let them land where they may, and then you just pick them up randomly, and if they're not sorted, you just do it again. So technically, it works, right? It only ends that loop when they're sorted. The time complexity, though, or how long it might take you, is a bit sketchy, to say the least. So there's an even worse version of it. It's called bozo sort. So bozo sort is even slightly worse. All it does is just randomly switches two cards, and then you check if it's sorted or not. If it's not sorted, you just keep on going. So we can actually implement that and see how it works. Spoiler alert, it doesn't work that well. So if we want to implement that, well, the hard part, or not hard part, is we need this in order function, which just tells us if that array is already in sorted order. So we can write that quite easily. So to check if an array is in order, we just go through all the pairs. In this case, I start at I equals 1 because I'm subtracting by 1 each time. Again, there's one fewer pairs than there are elements in the array. So I'll check the two pairs. If the pair to the, or if the number to the left is greater than the one to the right, I immediately know this is not sorted, so I can return false. If I inspect every pair and that doesn't happen, I know it is sorted. So in bozo sort, all I can do is just, while the array is not ordered, I can pick two random numbers. So if I do rand mod array length, that will give me a valid index in this array. And I have a little optimization here so I don't pick the exact same index. So I do another rand with array length -1, and then if the number I randomly picked is greater or equal to I will just bump it up by 1, so it essentially will make it so that j will just be a valid index in this array and it will not be equal to I, so I can make sure that I actually swap two values. And then I just swap them. That is the entire algorithm, if you could call it that. Do not use this on an exam if they tell you to use a sorting algorithm, even though it kind of works. Probably don't want to do it. So we can try and sort. In this case, let's try and use it. We can sort, what's this? Sort 9 numbers. So this again gets the array length, prints the array, calls bozo sort, and then prints the array. So if we compile and we run our bozo sort, we can see that, hey, it kind of worked. Well, it did work, miraculously enough. But, you know, computers are fast. We can do something more interesting and see how many times we had to swap two elements. So let's just create a variable called int count and just see how many swaps we had to make. So we can do ++ count. Printf bozo sort done in swaps. So let's see how long it actually took, because computers are deceptively quick. So we run that, it took, what, 1.5 million. So computers are quite quick, and that's kind of boring because it's doing it in the same number of times because, you know, RAND is not being even somewhat good. It's giving us the same numbers every time. So if we want to have more fun with it, we can do this, include time.h, and we can do srand. So before we do anything, we can use srand to try and make it a bit more random. So that will give us a random seed based off the current time. So it should give us a slightly different random numbers every time. So we can see that was done in, 200,000, pretty good. That was done in 400,000, 600,000. It kind of works. We can see it kind of break down. So let's add some more numbers to the end. So 40, 60, 87, 88. So what's that? That is 13 numbers. So compile, run it. Ooh, yeah. It's kind of struggling a little bit. My poor laptop. Okay, that might be a bit too much for it. All right, let's press the old Control-C and give it a little bit of help. Let's subtract a number. So run it. Hey, it worked this time. We got it in 2.9 million swaps, so pretty good. Run it again. Oh yeah, we are unlucky this time. Yikes. Yikes. So it does work-ish. It's kind of a joke sorting algorithm because, you know, only handles sorting on a good computer, like 12 things, which isn't the greatest. But hey, it kind of works. So that's something you should definitely never, ever, ever, ever use. I don't even know why I showed you it. I don't know. So if you want to use quicksort, generally you do not have to write your own quicksort. So I can show you how to use it. It is in the C standard library. Its function prototype is a bit scary, but we should kind of understand how to use it now since we've, you know, dynamically allocated arrays and all of that fun stuff. So this, they call it qsort, short for quicksort. Again, I don't know why they just shorten everything to the nth degree. And it takes 4 arguments. The last one is a bit weird that we haven't seen before. So it takes as the first argument a void star, so it's just a pointer to something that it doesn't know. Again, C is a bit silly. It's not that smart. It doesn't know generically what values you are pointing to because you could be pointing to anything. And they try and make it generic. So the arguments are, the first argument is called base. That's the starting address of the array to sort. The next one is called nmem. So that's the length of the array or the number of elements. They call it the number of members. Again, that's just what they like to call it. It means the exact same thing. And then the next argument, the size, is the size in bytes of each element. So you have to spell out exactly how big each element is, how many there are, and where the starting address of the array is. Because if you don't tell C all this information, it will access invalid memory and then something bad will happen. The last one is a very weird argument. So the argument name is called compare without an E at the end. And well, you don't know this yet, but functions are also specified by addresses. So this star compare means it's just an address, and that address is called compare, and the rest of it is a function prototype. So this means this compare address is a function, and the function has 2 arguments. The first being a const void star, so that is just a pointer, and the other one is another pointer, and that is just 2 pointers to elements. so we can actually compare them. And compare just actually returns an int. And the int it returns should be -1 if the first argument is less than the second, +1 if the first argument is greater than the second, and then 0 if the two elements are equal. And note, thankfully, this is the exact same as string comp, so you can actually use this to compare strings quite easily. So if we wanted to, let's show an example. So if we wanted to use quicksort to sort an array, well, we have an array as before, have the array length, so that's the number of elements of it, and then we use qsort. So the base is an array, so that address of the array. Number of members is the array length. The size is, well, it's an int array, so it's size of int. And then we have to write this compare function. So the compare function always gives us pointers to actual individual elements in the array. So there'll be 2 pointers to ints, and we should actually use their values. So in this case, with C, you have to do a bunch of random typecasting because, again, C can't generically know what your values you're pointing to. So they have to be const void stars, which means I can do whatever I want with the address itself, but I won't change any of the data through it. So the first thing we have to do is cast that pointer because it's actually pointing to an int, and we can add a const to it because this function should not modify any values. It's just comparing them. So we can dereference that after we typecast it to get the value because, well, we actually just care about comparing the values. So I can do that for x and y just to get 2 values. And then if x, which is the first argument, is less than y, I can return -1. That's what it says. If x is greater than y, I can return 1. So that means it's greater than it. Otherwise, the 2 values are the same. I can return just 0. So if I compile that and run that, and if I compile that and use that, I can see that, hey, it does indeed work. It's kind of ugly, but it saves us from writing the quicksort, and they optimized it. It's a lot faster than anything you can probably write by hand. So you can use this if for some reason on exam you have to sort. If you want to, you can use this instead of writing, I don't know, your own sorting algorithm if we don't give you one. It's kind of up to you. It's kind of ugly for sorting a whole bunch of different integers, but if I want, I can actually sort like all the program arguments. So let's go here. So if I go here and let's say I just want to type a whole bunch of program arguments. So let's go ahead, compile. So say in sort args, I just want to type a whole bunch of like ABC, AAA, John, Elf, something like that. And I want to see all these strings in sorted order. So right now it's just in the same order that I typed them into my program. Well, I can just go ahead and use qsort. So the first argument at 0 is always the name of the program, so I want to skip that. So I want to sort the remaining argument, so I can do some pointer arithmetic here, argv +1, so that will move it forward 1. And then the number of members is, I'm skipping one of the arguments, so it's argc -1. And then the size of, well, they're given by C strings, so they are pointers to chars. They're const. We're not going to modify their values or anything, so I can use size of that. And then the tricky thing is the compare function because it gets a bit ugly. So if I'm pointing to actual individual elements here, well, my element is a const char, right? So The compare function gives you pointers to the element, so this will be that whole double pointer thing. So the arguments I actually get are a const char star star, so a pointer to an int, and if I dereference it, that will actually give me the pointer which represents my C string. But if I just want to break down the typecasting, this is what it is. So this is A, this is B. And then, thankfully, I don't have to compare them or anything. All you need to know in this is that, like, if I dereference X, that will give me a pointer to a char of const. So that's my normal C string. So since that's my normal C string, I can go ahead and just use strcomp. So I can use strcomp, dereference X, that gives me the first value, dereference Y, that gives me the second value, and strcomp actually returns the correct values with what I want. So if I compile and run this now, boom, it is now in sorted order. So it will go ahead, sort all the C strings for me. I don't have to worry about even writing my compare function. I don't have to worry about writing quicksort or anything of that nature. So I can see specifically it sorted that, and that's basically what your File Explorer or your Windows Explorer or Finder or whatever will do to display files for you in sorted order. It will just do something like that. Again, it will use a string compare function, which is why sometimes you sort stuff, it will be in strange orders, because it goes by ASCII values. So, any questions about that? Random, yeah, this whole lecture is kind of random aside because we are kind of ahead. So, most of the time, you will use sorting algorithms instead of writing them. Writing sorting algorithms, they're good practice in C, but because, small errors produce the wrong result, or memory errors, everyone has lots of fun debugging, segmentation faults and things of that nature. Qsort, in terms of programming languages, that's the most difficult sorting function to use, since you really have to understand memory, the limitations of C, how much space things take up in memory, what memory even is. Some programming languages try to hide that from you. So that is why we use C in this course, because, well, you'll be doing hardware in like 243. So you actually understand how programming works, and this is as painful as sorting will get for you, because C has to use void star to be general and support pointing to a whole bunch of different types. In 244, you'll use C++. The primary design goal of C++ was to make operations like sorting easier to use and more efficient. So in them, you'll be able to do something like just array.sort, or Python, you can do array.sort, and it will just magically work. But under the hood, it's going to have to do all of these same things, do all the same compares, use all the same algorithms, but other programming languages make it a lot easier to actually use, which I know kind of makes sense because C was created in like the 70s. So thankfully we have kind of moved on from there, but it's still a very small, simple language that actually teaches you how a computer actually works, even though the memory issues are, a pain to debug. Believe it or not, they are building character. So, any other questions? It is a short lecture today. Again, this was kind of, slightly out of scope because we, again, are ahead. We're closing in on the end of the course. The last content lecture you'll probably be responsible for is next Monday. And then after that, we'll just have kind of more fun lectures that you can hopefully write programs that are a bit more useful. So with that, wow, we really went fast. So yeah, we've kind of been slowly getting ahead of the other lectures anyway, so that makes sense. So I'll just hang around here in case you have any questions. So just remember, pulling for you, we're on this together.